This is problem 40. In this problem, a 50-gram bullet and an electron are both measured with a speed of 300 meters per second with a precision of 0.01%. In part A, we want to know what the minimum uncertainty in the bullet's location is. So for this problem, we're using Heisenberg's uncertainty principle. So we have the uncertainty in the position times the uncertainty in the momentum must be greater than or equal to h bar over 2. We can look up h bar in the appendix in the back of the book. H is given to us in the appendix and also h bar. There is a relationship between them. H bar is just equal to h divided by 2 pi. If you look up h bar in the appendix in the back of the book, it's not written quite correctly here, so this is h with a line through it. It's supposed to be written with the line higher up. So we'll leave that for later. In part A, we want to know what is the minimum uncertainty in the bullet's location. So if the uncertainty in x times the uncertainty in the momentum is greater than or equal to h bar over 2, then the minimum uncertainty for x times the uncertainty in the momentum would be equal to h bar over 2. And from that, we can say the minimum uncertainty in the position is equal to h bar divided by 2 times the uncertainty in the momentum. So I can look up h bar, and I just need to find the uncertainty in the momentum. The uncertainty in the momentum is equal to the momentum times the precision of 0.01. We can use classical methods to find the momentum. So the momentum is equal to the mass times the velocity. It's a 50-gram bullet, so that's 0.05 kilograms times the speed of 300 meters per second, and that gives us 15 kilograms times meters per second for the momentum. The uncertainty in the momentum is equal to 0.01% of that. So for the uncertainty in the momentum, I get 0.0015 kilograms times meters per second, because this is p times 0.0001. So now I can go ahead and use this equation to find the minimum uncertainty in x. Because I have the uncertainty in the momentum in kilograms times meters per second, for h bar, I want to use 1.055 times 10 to the negative 34th joules times seconds, rather than using the one in electron volts times seconds. So I have 1.055 times 10 to the negative 34th joules times seconds divided by 2 divided by the uncertainty in the momentum, which is 0.0015 kilograms times meters per second. And this gives me 2.52 times 10 to the negative 32. A joule, let's do this up here. A joule is a Newton times a meter. So this is a Newton times a meter times a second divided by kilograms times meters per second. A Newton is a kilogram times a meter per second squared. So this is equal to kilograms times meters per second squared times meters times seconds divided by kilograms times meters per second. So the meters here cancel out. I have second squared here. This would be a second in the numerator. So this and this cancel out, and the kilograms cancel out, and this leaves me with units of meters. This was supposed to be 3.52. So this is our answer for part A. For part B, we will also want to find the minimum uncertainty in the position, but we want to do this for the electron. So we have the same equation that we had here. The minimum uncertainty in the position is h bar divided by 2 times the uncertainty in the momentum. So for this, we are going to use relativistic methods to find the momentum. So we have Pc is equal to gamma times mc squared times v over c, but v is much less than the speed of light, so gamma is approximately equal to 1, so Pc is approximately equal to mc squared times v over c. So this is an electron, and so mc squared is equal to 511 kilo electron volts. So for Pc, I have 511 kilo electron volts times 300 meters per second divided by the speed of light. And this gives me in electron volts 0.5114. Now I want to find the uncertainty in the momentum, but I have Pc here, so actually I'm going to take this equation here and multiply in the numerator and the denominator by c, so I have x-min is equal to, this would be h bar times c divided by 2 times the uncertainty in Pc. So now I can take Pc and multiply it by the 0.01 to get the uncertainty in Pc. So this is 0.5114 electron volts times 0.01% as a decimal is 0.0001. And this is 0.00005114 electron volts. And I can also look up h bar c in the appendix. This time, h bar is written correctly with the line up here where it should be. And this is 197.4 electron volt nanometers. So 197.4 electron volt nanometers divided by 2 times 0.00005114 electron volts. The electron volts cancel out, and this gives us for the minimum uncertainty in X 1.930 millimeters, which is much larger than the 3.52 times 10 to the negative 32 meters that we found in part A. In part C, they ask us, for which object does the Heisenberg uncertainty principle have a larger effect on our knowledge of the object's location? So this would be for the electron. And this is because, well, we found the uncertainty in Pc rather than the uncertainty in the momentum, and we have it in different units also. But the reason that the uncertainty is larger for the electron, the uncertainty in X, the minimum uncertainty in X is larger for the electron, is because the uncertainty for the momentum is smaller for the electron. So that concludes problem 40.